Hi guys. So as we start working with this sort of abstract idea of the electric potential, I want to take a moment and connect back to something from PH2011, and that's the connection between potential energy and work done by conservative forces. So the hope is that this might give you something that's a little more familiar. So recall conservative forces. Uh, i.e., forces that are path independent. They only depend on the position. So, of which, gravity was the one that we worked with in 2011, and the electric force that we're talking about now is the same uh, animal. So, with these kinds of forces, if you have a change in potential energy, it'll be equal to the negative work done by a conservative force. So let's think about gravity. Um, we got pretty familiar with the idea if you have like an object, a box or something, and you move it up some height, all this h, um, that, let's say we're moving this from A to B, and we've set our coordinate system here so that A is at 0. Um, the change in potential energy from this, you know that that's mgh, or mgh minus mg at 0. And that's going to be equal to the negative work uh, done by gravity. And remember our definition of work is F dot D. So now the work that's done by gravity, notice the force of gravity is pointing down. So when you go to take this dot product between F and D, the force of gravity is pointing down, but the change in the displacement is pointing up. And provided these things are, they're along the same direction, but they're anti-parallel. So what this means is that this would be mg dot h. Think of the directions here. So that, just to be real explicit, gravity is pointing down, but h is pointing up. So as a result, there's a negative sign here. And so it gives us the familiar mgh. So this is done by looking at the work. Now, we can connect this explicitly to this idea of potential by recognizing that the potential is equal to the potential energy per unit charge. So let's look at a situation that's very similar to this gravitational situation. Um, oh, whoops. So, and that is our electric field. So remember, with the deflection lab, we had these two plates and we had a approximately constant electric field between them. And we can do kind of the same exact thing. So imagine that you have a charge and we're going to move it some h, um, from A to B here. And, our coordinate system will set the 0 at A. Now, and you can think of that as also the potential at A is 0. So we can look now at the change in potential. It would be, potential at B minus the potential at A. That's going to be equal to the negative work done by the electric force per unit charge. So, and we have a handy quantity that's the electric force per unit charge, and that's the electric field. So this would look like negative electric force dot H per Q. So, and now this is the electric field, electric force per Q. So this becomes E dot H. Now notice the electric field is pointing down. Our H that we're moving through is pointing up. The displacement that we're moving through is pointed up. So these are anti-parallel again. So when you take the dot product, you would pick up a negative sign. This becomes negative EH, EH. And where this gets interesting now is if we think about connecting this back to potential energy. So this gets interesting when we connect back. So, and why is because, so the change in potential energy is just the charge times the change in potential. But the issue is that while mass can only be positive, charge can be both positive and negative. So as a consequence, and maybe to help visualize this, remember these electric field lines go from positive to negative. So if the charge was positive and you move it from A to B, as in our picture, the change in potential is positive, and the change in potential energy would also be positive. And you can kind of imagine that because a positive charge is not going to want to be forced close to other positive charges at B, and so it would require energy to do that. So you would be increasing the potential energy of the situation. Now, alternatively, if you had a negative charge, you do the same thing. You move it from A to B. The change in potential isn't affected. It's the same situation. Would still be positive, but the change in potential energy, on the other hand, would be negative. And you can visualize that. If you had a negative charge, it's going to want to get away from these negative charges, and it's going to be attracted to those positive charges, and that would release energy. So it would be losing potential energy. So hopefully this comparison to gravity is helpful to kind of visualize potential and this connection to work. But be cautious because it's a little more complicated with the fact that charge can be both positive and negative. And also be careful about what direction you're going, as the direction is going to impact the sign. So let me show you what I mean. If instead we had decided to go from high potential to low potential, i.e. From B to A, this would look like VA minus VB. And when we go to compute this, so this would be E dot H. Now in this case, both E and H would be pointed down. They would be aligned. So this would become negative EH, and it's going to differ by a sign compared to what we got above. So, but this is consistent because in this case, our change in potential is negative. So keep an eye on that issue if you're going from high to low or low to high. That can kind of get us tripped up.